In the previous lecture, we went through the prerequisites for statics. We said that knowing how to add and subtract vectors and calculating the dot product and cross product of vectors is all we need to dive into statics. In this lecture, we get right into statics. We start by asking this question, what is statics about? Well, statics is all about Newton's first law of motion. What is Newton's first law of motion? Well, here is the first law. If the sum of all the forces exerted on an object is zero, then the object will be at rest or in uniform motion. So imagine that we have an object like a piece of rock or a stone, and bunch of forces are exerted on the object. Newton's first law says that if the sum of all these forces is equal to zero, then the object will remain at rest or in uniform motion. We will explain this uniform motion part in a minute, but right now you can just think about the object being at rest. Note that the first law of motion is a two-way street, so if an object is at rest, then that means the sum of all the forces exerted on the object is zero. And this is exactly what we are going to have in statics. In all the problems in statics, they tell us an object is at rest and we need to sum up a bunch of forces and equate them to zero. Some of those vectors would be unknown, which we will find them by solving this equation. So all we need to do in statics is to add up some force vectors. That's it. Now let's see what is the deal with the uniform motion. What we mean by uniform motion is moving on a straight line with constant speed. This definition allows us to rephrase the first law in the following format. If the sum of all the forces acting on an object is equal to zero, then the object velocity will remain constant. So let's say that we have our object initially at rest, then bunch of forces are exerted on the object. If sum of all these forces is equal to zero, then the object remains at rest. If the object was initially moving with constant speed on a straight line, and then those forces were applied, the object will keep its motion with the same velocity on the straight line. So this was Newton's first law of motion and its mathematical form. As we said, statics is all about Newton's first law of motion. Well, what about the second and third law of motion? I think here is a good place to review those laws quickly. Well, the second law says that if the net force sum of F is exerted on an object with mass m, then the object changes its velocity with the rate of sum of F over m. To state the second law in mathematical form, we need to define acceleration, which is change in velocity vector over time. So basically, the acceleration is delta v over delta t. With this definition, the second law can be expressed as acceleration is equal to sum of F over m, or in more familiar format, sum of F is equal to m times a. So this was Newton's second law, and we will study it extensively in dynamics. Notice that one can say the first law is kind of the special case of the second law in the following sense. If you put sum of the forces equal to zero, then from the second law we conclude that the acceleration is equal to zero, which means that the velocity vector doesn't change, or in other words, v is constant, and this is exactly the first law, right? Well, here is a side note. Newton's first law is not actually a special case of the second law. So here's one way to make the argument. Newton was a smart guy. Why would he start his three laws of motion by a special case of his second law? I bet you can have some fun asking this question from your professor in the class. Side note 2. We should use the first law to establish what an inertial frame is. The second law is only true in inertial frames of reference. I don't want to get into the topic of inertial frames and explaining why the first and second laws are actually two separate things. I don't want to do so because I'm assuming that this is just a quick review of Newton's laws of motion, and it is not the first time you are being introduced to them. And also, as far as we are concerned in statics, it really doesn't make a difference for us. With that being said, for those of you who are interested, I recommend you to watch this 30 minutes video on the frames of reference, which I leave its link in the description. Okay, moving on. Let's get into the third law. Well, Newton tells us in his third law that for every action there is an equal and opposite reaction. To explain this, consider two objects, A and B. If object B exerts the force F sub BA on object A, the third law says that as a reaction, object A will exert the force F sub AB on object B. The magnitude of the reaction force is equal to the magnitude of the action force, but in the opposite direction. In mathematical form, we show this by writing F sub AB is equal to minus F sub BA. This vector equation tells us the same thing. The magnitude of the two forces are equal, but they are in the opposite direction of each other. We will use the third law in both statics and dynamics from time to time. So this was basically lecture 2, and now let's review some fun stuff. I want to add this part one more thing to some of the videos to mention interesting, fun or related stuff just to have some fun. The first thing that I want to mention is the use of Newton's law, not just in physics or mechanics, but in conversational everyday life. For example, Newton's first law comes up to explain the concept of inertia, which is the object's tendency to keep their natural state, i.e. being at rest or moving with a constant velocity. So we say objects resist to change their natural state because of inertia. But in an everyday context, the first law is used to explain the resistance against any change in general. So you might want to change a bad habit of yourself, and you see that it is very hard, especially at the beginning. So you say, I guess inertia doesn't let me to change my bad habit.
Man, if we had money, why'd we keep it? You know, why'd we have to have the world's shittiest RV? Inertia? Yeah. Yeah. Inertia. So, hey.
The third law, which says for every action there is an equal but opposite reaction, is used in everyday life too. For example, it is used to explain backlashes when you want to bring a change to a society or an organization. Okay, the next thing is that it is often said that Newton was living 3 hours away from the sea, but he never went to see the sea. And this seems strange because Newton was a smart fella. He was great at observing the natural world around him and doing experiments. I mean, he was doing experiments even with his own eye and needle when he was working on light. So you would expect such a person to be interested to see the sea at least once. So is this true that he never went to the beach? Well, let's first see if he was close to the beach. He was born in Lincolnshire in England. We know that he went to the Cambridge University at Cambridge, and he also went to London. Those places are not that far from the sea. With a buggy and horse, it could have taken him just a few hours to see the sea. He could have even walked to the beach, although that would have taken him probably 2 days, walking 10 hours each day. Yeah, that's a lot, but not for the guy whose experiments involves his eyes and a needle, right? Well, from what I could find, it seems that he didn't bother to go and see the sea. However, there are stories of him taking a small boat to cross the River Thames in London. And the final question here is that, did Isaac Newton die a virgin? Well, according to Wikipedia and New York Times, there is a possibility that Newton was never engaged in a romantic relationship.
Isaac Newton died a virgin. That means I have one up on history's greatest scientific genius. Because I'm not dead.
There are lots of trolls about Newton. I find these few very funny. And with this, we conclude this lecture.